We're talking about energy. We're going to start this off with a couple of introductory ideas or basic concepts. And the main point of all of this is the energy is the stuff, whatever that stuff is, that allows us to generate force. And the main idea is this: the amount of stuff that I use equals the amount of stuff something else gets. And my favorite example of this is the amount of stuff the pitcher applies to the baseball equals the amount of stuff that the baseball gets. So when I pitch, I do something to the baseball. However much stuff I do to the baseball, that's how much stuff the baseball gets. Okay? However much I do to the baseball, that's how much the baseball gets. Okay? So that's the first thing. Force and energy are connected by a concept called work. Okay? And this isn't work the way you think of work. It's not mental work in any way, shape, or form. It's sort of like physical work, but it's got a very specific definition. But force and energy are connected by the concept of work in the same way that motion and force are connected by the concept of acceleration. And what we say is the amount of force applied to an object over a distance is the work, okay? So if I used a force of 50 newtons and applied that to a baseball over a distance of 1 meter, that's about right, isn't it? When I pitch, the length of the force on the baseball is about 1 meter, so that's a pretty good example. If I apply a force of 50 newtons over a distance of 1 meter, that is the amount of work that I did on it. Okay, now you can say then that if I multiply 50 newtons times 1 meter, that would be 50 Newton meters. But we give that unit a special name. Does anybody know what units we use for force or for energy? Joules. That would mean that I have 50 joules. I applied 50 joules of work to the baseball. Since I applied 50 joules of work to the baseball now has 50 joules of kinetic energy, for the energy of motion. Okay, that's what I mean by the amount of stuff I apply to the baseball is the amount of stuff that it gets. I did 50 joules of work on the baseball, and now the baseball has 50 joules of kinetic energy. Okay, so by knowing the amount of motion I gained, I should be able to determine the amount of force applied, and in turn the amount of energy required to create that amount of force. Then, the amount of energy that's available to do things is conserved. The fact that I'm 1,500 meters up a mountain provides me with a certain amount of stuff to be able to do work. And if I'm 1,500 meters up a mountain, what do we call the stuff that I have that I can do work with? What kind of energy? Potential energy, right? Since I'm 1,500 meters up or above the surface of the earth, I have the ability to do the amount of work that it took me to get me up that 1,500 meters. If no forces oppose me coming down the mountain, it doesn't matter what path I take to get down the mountain, the amount of stuff I have at the bottom of the mountain equals the amount of stuff that I started with at the top. Okay, so let's kind of illustrate that. I'm here up on the mountain. I'm 1,500 meters up on the mountain. And first of all, if I just drop straight down and I say that there's no resistance, no air resistance at all, no friction in any way, that however much potential energy I have up here, That's the amount of kinetic energy that I'm going to have down at the bottom. Okay, so we're going to see that this conservation of energy allows us to provide yet another way to solve a bunch of problems. So if I know I have this much energy here, I've got the same amount of energy when I hit the ground down here. It's however many joules of potential energy is now the same number of joules of kinetic energy at the bottom. Now, the interesting thing about this is, if there is no friction, if I slide down the mountain in whatever path I take, when I get to the bottom, if there's no friction in my sliding, I will still have the same amount of kinetic energy as the amount of potential energy I started. What's our favorite example of that kind of an idea? Or what's the funnest example of that kind of an idea? Maybe a roller coaster? Okay, I go to the top here, and I've got a tremendous amount of potential energy, and we do everything we can to limit the amount of friction that we have on the roller coaster. Now, obviously, we lose some energy on the way down, but technically, if there was no friction, we could go up and down and up and down and up and down and up and down as many times as we wanted, and if there was no friction, I would have the same amount of kinetic energy at the bottom as I have potential energy at the stop. They have to use some pretty significant braking at the end of the ride in order to get us to stop, right? So we've got a lot of kinetic energy at the bottom, and if there was no friction, it would be the same amount as the potential energy at the top. So this concept will allow us to solve many problems. It would be much more difficult to solve if we had to analyze the forces. Okay, so work done by a constant force. We want to find out how this concept of work works. Okay, so we've said that work equals force times the distance. Notice I put a little parallel sign here. So if I accomplish a certain amount of work by pulling up on a box, right? If I'm pulling a box along by a rope, okay, not all of my force is in the direction of my motion, is it? So what this little sign here means is that I can only count the amount of force that's in the direction of my motion. Okay? I might have 100 newtons of force here, but let's say this angle is 30 degrees. Okay, this angle is 30 degrees, and this is the adjacent side of that angle. To find out the force that I'm applying in the direction of motion, I'm going to have to multiply force times the cosine of theta. Okay, and since I know that the cosine of 30 degrees is 0.8666, I know that I have about force applied in the horizontal direction is going to be 86.7 newtons. Okay, so I can only count that 86.7 newtons in my calculation of the force, or of the work. Okay, and this little parallel sign here means the force parallel to the direction of motion. The force parallel to the direction of motion. Or I could just say FD cosine of theta. Okay, so if I have that force then, that 86.7 newtons, and I apply it over a distance of 10 newtons or 10 meters, I will have done 867 joules of work on that box. Now, here's the problem. If I do this, that 867 joules of work is going to go to waste because I've got friction in the opposite direction. And friction is going to oppose this work that I'm doing friction is going to oppose this work that I'm doing. And I can, if I don't count the time period of when the box is starting to get into motion or the time period where the box comes to a stop, and I suggest that I'm pulling this box at a constant velocity, and I don't count that point in time where I started it and where it stops. While it's in a constant velocity, I know that the amount of work that friction is doing on it in the opposite direction is going to be 867 joules as well. Okay, now I'm clearly ignoring the fact that I had to get it up to a constant velocity and then it stopped after I stopped pulling on it. But while I was pulling on it, while I did this 867 joules of work, since I was going at a constant velocity with this, friction was doing exactly the same amount of work in the opposite direction on the box. Okay? Doesn't mean the box isn't moving, it means the box is not accelerating. Just like with forces, right? If I have a balanced force, it doesn't mean that the object's not moving. If I have a net force of 0, it doesn't mean that the object's not moving, it means it's not accelerating. Same thing with work. Okay, so force is constant, and only the component of force in the direction of the motion counts. You can exert a force on an object, but if there is no more motion or force is not in the direction of the motion, you are not doing work on it. We're only going to consider translational motion right now. We're not going to consider angular motion or motion around a circle. The object is rigid. It can be considered a particle. Work is a scalar quantity. It doesn't have direction. Okay? And what I mean by that is that I can't do vector addition on work. I can't say if I have a certain amount of joules of work in that direction and a certain amount of joules of work in that direction, then I have that amount of work. I can't do that because it's not a vector quantity. If that was a force, I could do that. If it was a velocity, I could do that, but it's not. Okay, so work is a scalar quantity. But I can say that there is work being applied to the object in the opposite direction of its motion. So if I am doing work on an object and friction is doing work on the object in the opposite direction, even though it's not really the same thing as vector addition, we're saying that I've got one component of work in in a positive direction and one in a negative direction. And we'll see how that works. Positive work done on an object in the direction of motion. Negative work done on an object opposing the direction of motion. And it's important to ask if work is done by an object or on an object. And we'll see what that means as well. Okay. It's also important to ask if work being done is being accomplished by an individual force or a net force. And the units are joules. Okay, just a reminder, we can always know what the units of newtons are because we know that force is mass times acceleration, which is kilograms times meters per second squared, right? So we always know that newtons are kilogram meters per second squared. Since joules are newton meters, if I add an additional meter there, joules are kilogram meters squared per second squared. Okay, so we should always be able to figure out, if we forget what those individual units are, it's nice that we have names for these things, but it's also important that we understand what the actual units are, kilogram meters squared per second squared. So, person pulls 50 kilogram crate, 40 meters along a horizontal floor by a constant force, an applied force of 100 newtons, which acts at a 37-degree angle. The floor is rough and exerts a friction force of 50 newtons. Determine the work done by each force acting on the crate and the net work done on the crate. Draw a free body diagram separately to show just the forces acting on the crate. Okay, so if I have my free body here, what are my forces? Gravity, force due to gravity. I know that that's equal to mg. That may or may not be important here. What other forces?
Friction.
I've got a friction force of 50 newtons opposing the motion of the box. Force of friction equals 50 newtons in the opposite direction. What are my other forces?
Force applied.
Okay. I have an applied force at an angle of 37 degrees of 100 newtons. What other force do I have? I'm on a surface, aren't I? So what other force do I have?
Net neutral.
Come on, what's the name of that?
Normal force.
It's the normal force. Okay, but the normal force is not going to be the same as the force due to gravity because I've got a component of force acting in the positive direction as well. So if I were to think about the normal, or if I were to think about the normal force, I would end up having to think that in the y direction, the net force, which I know because it's not accelerating either up or down, is what? What's the net force in the y direction? Zero, right? There is no net force in the up and down direction, right? It's not accelerating either up or down. In fact, it's not moving in the up or down direction. So I know that that's going to be the force due to gravity, or mg, minus the normal force. And I know that the other vertical force is going to be Fa in the vertical direction equals force A times the sine of theta, right? So I know that the force due to gravity is going to be balanced by the sum of these two things. So if I wanted to, and I don't need to here, but if I wanted to, I could find out what all of these different forces were, minus force applied times the sine of theta. Right? So I could figure these things out. Okay? I want to know what the net work done on the crate is. The direction of the motion is going to be in the positive direction, right? The horizontal direction. And so I also know that I need to figure out the force applied in the horizontal direction. And I know that's going to be the force applied times cosine of theta. And I do need to know that. So that's going to be 100 newtons times this cosine of 37 degrees. And if someone could figure that out for me.
Uh, 79.9.
So 80 newtons.
Yeah.
Let's say 80 newtons. Okay. So I want to know what the net force is. I want to know what the net work is. Determine the work done by each force acting on the crate. Okay. So the applied force in the horizontal direction. Work applied in the horizontal direction. It's going to be force applied in the horizontal direction times the distance. Now, let's be careful how we approach this because we've got two different ways that we can approach this. If I just do it this way, force applied in the horizontal direction is 80 newtons. And the distance was 40 meters.
Yeah.
So my applied force did 320 newtons of I'm sorry, 320 joules of work in the positive direction. Now, how else could I have done this? What did I say that my work formula actually is? I didn't say that it's just FD. What did I say that it was? FD what?
Cosine theta.
FD cosine of theta. Okay, so in general, we should not take this approach because our formula already does that for us. Okay, don't end up multiplying times the cosine of theta 2 times. Okay, here we already took into account that the FA cosine of theta was the force in the horizontal direction. We already took into account by finding that out. So what I should do is say 100 newtons times 40 meters times the cosine of theta. And we just take care of all of it in one action. Okay? We just take care of all of that in one action. I get the same thing, right? I get 320 joules. Okay? So, it's important to know that when we're thinking about this, we're always going to be doing this formula. Okay? Now, what if all of my force had been in the horizontal direction? This still works. Let's suppose that instead of having 100 newtons at 37 degrees, I have 100 newtons at the horizontal direction, or at 0 degrees. We would say the force applied, or the work applied in the horizontal direction is still FD cosine of theta equals 100 newtons times 40 meters. What's the cosine of 0 degrees? If all of my force is in the same direction as motion, the cosine of 0 degrees is what? It's 1. So see how that works? If all of my force is in the direction of motion, cosine of theta is 1, so all of my force counts. Okay? What happens if my force is perpendicular to the direction of motion? If my force is perpendicular to the direction of motion, what's the cosine of 90 degrees?
That's
0.
0. So none of my force counts. So if I've got a force that's perpendicular to my direction of motion, it is not applying work in any way, shape, or form. Check this out. I have the moon rotating around the earth. What's the direction of the force of gravity on the moon?
N. Like 1/0.
Straight down, right? What's the direction of motion of the moon at that point? The direction of motion of the moon at that instant is exactly perpendicular to the force of gravity. Is the force of gravity actually doing any work on the moon? It's not doing any work on the moon because none of the force of gravity is in the direction of motion of the moon. That's just like, right? Okay, now we didn't quite finish this problem. We wanted to Determine the work done by each force acting on the crate. So we need to consider the force of friction. Okay, so the work done by friction equals, and we're going to follow this procedure here instead of that one. The work done by friction equals the force of friction times the distance times the cosine of theta equals 50 newtons times 40 meters. But what is the angle of the force of friction compared to the direction of motion?
Negative one? Oh, my 80.
It's 180 degrees. What's the cosine of 180 degrees?
Negative 1.
Negative 1. Isn't it cool how that works? This formula covers everything. Okay? This is one of the only circumstances where we'll ever think about angles greater than 90 degrees for our calculations, because it works this way, right? The force of friction means that in the opposite direction means that I'm doing negative 200 joules of work. So my net work, my overall work, equals 320 joules plus negative 200 joules, and I can't write any more there, equals a positive 120 joules. My net work is positive 120 joules. What that means is that the box must be accelerating. Okay? Because I have a non-zero value for the net work. So whatever applied force this is, it's going to be causing this crate to accelerate. And obviously, we'll need to be able to figure out how much it's causing it to accelerate at some point. Any questions about what we've talked about here? Hopefully you can see what the relationship between the direction of motion and the work is. Okay. Determine the work a hiker must do on a 15-kilogram backpack to carry it up a hill of height 10 meters. Determine also the work done by gravity on the backpack and the net work done on the backpack. For simplicity, assume the motion is smooth and at a constant velocity. This already tells you that the net work is going to be what? 0, because this is going to be done at a constant velocity. Okay? So determine the work a hiker must do on a 15-kilogram backpack to carry it up a hill of height 10 meters. And we don't care whether it's done at this angle or this angle or this angle or this angle or this angle. The only thing that matters is that this height is 10 meters. Okay? I'm going to be doing the same amount of work no matter what angle I'm doing this at because of the addition of the cosine of theta to my formula. Okay, let's see if we can prove that. Okay, so my work formula, determine the work a hiker must do. Work equals force times distance times the cosine of theta. Okay, and first of all, the force that I'm going to need to use to carry a 15-kilogram backpack upwards against gravity is going to be determined by what? What's the force going to be? What's the force of gravity on the backpack?
MG.
mg. Okay? So if I carry it up at a constant velocity, if I'm going up at a constant velocity, if I carry it up at a constant velocity, I'm not accelerating, right? So I'm working against the force due to gravity. So mg is also going to be this force. My applied force is going to be mg. Cosine of theta. And if we say 15, and let's use 10 meters per second squared for simplicity's sake here. And I'm going up 10 meters. And let's say that we're actually going straight up. Let's say that we're pulling straight up. Somehow we're doing this. Maybe the stairs in the side of the hill are almost completely vertical. Okay. Let's assume that it is straight up. My direction of motion is up. My direction of the force applied is also up. So what's the degree of separation between the direction of motion and the force? Direction of motion and the force I'm applying are in the same direction, right? What's the degree of separation of those two lines? 0. So in that case, it would be times 1, right? Cosine of theta would be 1. So 15 times 10 times 10 is going to be 1,500 joules of work. I had to do 1,500 joules of work in order to accomplish that. Okay? Now, let's say that the angle that I'm carrying this up, okay, let's say that I'm at this angle, and let's say that this angle here is 30 degrees. Okay, this angle would be 60 degrees. Okay, and so what's the direction of motion? The direction of motion is this, right? Okay, the direction of motion is this direction. What's the direction of the force on the backpack? The direction of force on the backpack is still straight up. Okay? If it's hanging on my back, okay, it's being pushed upwards. So if we actually look beyond this a little bit, there's the direction of motion, there's the direction of force. So the degree of separation between my motion and my force is actually 60 degrees. It's not 30 degrees, okay, it's actually 60 degrees. Okay, so we have to be really careful about that. The direction of motion here is that the direction of the force is against gravity. Okay, so now I'm going to say the work is still 15 times 10 meters per second squared times, but how many meters am I going in the direction of motion? If this is a 10 meter height, okay, so I need to use the hypotenuse, so hypotenuse, opposite side. So I can say that the length of the hypotenuse is going to be, so sine of theta is opposite over hypotenuse. And so the hypotenuse is the opposite side over the sine of theta. and the sine of 30 degrees is 1/2. The opposite side is 10. So 10 divided by 0.5 is going to be 20. So the length of this is going to be 20 meters. And the cosine of that 60-degree angle here is going to be 1/2. So the amount of work still works out to be 1,500 joules. Okay? It doesn't matter what path I take to get to this point. If I go straight up, I do 1,500 joules of work. If I go along this path, I do 1,500 joules of work. If I go along this path, it would still work out to be 1,500 joules. Okay? The key thing is how much of my force is in the direction of motion. How much of my force is in the direction of motion? And we're going to find that by using the cosine, but we have to make sure we're using the right angle. Okay? The moon revolves around the Earth in a nearly circular orbit, kept there by the gravitational force exerted by the Earth. Does the gravity do positive work, negative work, or no work on the moon? We already figured it out, right? What did we say?
No work.
Does no work. Because the force is not in the direction of the motion. Okay. Now, here's where we cross a little bit into the idea of calculus. Have you started doing integrals yet? You're still dealing with derivatives?
Yeah.
Okay.
We're doing like critical numbers and like maximum and
Maxima and minima.
yeah.
And yeah, where does it change direction and
Yeah.
that kind of thing? Okay. So, okay, this relates more to the idea of an integral. Okay? So we'll give you a little bit of an advance notice here. Now, why did that happen? Okay, so work done by a variable force. Now, our curriculum is such that you won't end up doing problems related to a variable force, but you need to know the concepts. So the force applied to accomplish work is often not a constant force, but in order to use the above equation to calculate work, the force needs to be constant. Now, for example, when I go to push on something, let's say I could move this, I have to be able to move this in order for it to be considered work, right? If distance is 0, I don't do any work. I can push on this all day, and you would say, well, yeah, you're doing work, you're pushing on it, you're using a force, but no, I'm not moving at any distance, so I'm not doing any work on it. Okay, it's got to move in order to accomplish that. But when I go to push something, the instant I start pushing, am I at the maximum amount of force that I'm using, right? I'm not, am I? I start with just a gentle touch, but then as I use more force, I get to a point where I have a maximum amount, and then as I start to back off, the amount of force backs off as well. So normally a force applied to an object is more like this, okay? As I begin to push, I push with more force until I reach a maximum, and then I continue to push with that force, and then as I let go, the force backs off. So normally, we don't really have anything like a constant force. It's not a real thing, okay? The force needs to be constant. if we know a mathematical relationship that describes how the force varies over the distance the force is applied, we can use the calculus process of integration to determine work. But if I don't know how the force varies, the best we can do is an estimate based on the graphing of the force versus the distance over which the force is applied. And here's how this is going to work. If this line represents the amount of force that I apply over a certain distance. So as I begin pushing it, the force is less. As I begin pushing it, the force is less. But the further I push it, the greater the force I exert here. Okay? And you can see that this is some kind of a curve, and there may be a mathematical formula that describes that curve. There may not be. But notice that on the left side here, I have force, and on the bottom here, I have distance. Force times distance is work. You agree? Okay, so the area under this curve is the amount of work that I did. Whatever the number of units of area that are under this curve, it should extend all the way here, that is the amount of force that I use, because force times distance is the amount of work. So if I can figure out what the area under the curve is, I can figure out how much work I did. The best we can do is draw a bunch of little rectangles here. I know how to find the area of a rectangle, right? It's width times height, right? So width times height. So if I choose my rectangles so that as much of it is above the curve, as much of it is below the curve, my rectangle very closely approximates the amount of area that I have here. And I do that again, and I find the area of that rectangle, and I do that again and find the area of that rectangle, and then find the area of that rectangle, and then I add all the rectangles together. Okay, so in that way I can estimate the amount of area under the curve, or because we're only doing it from dA to dB, I can figure out how much work was done over that time, the total amount of work that was done. Okay, and then I could use that in my calculations. Now, you'll never have to do that, but you need to understand that concept. And what calculus does is they're going to say, well, what if we shrink the size of our rectangle so that it becomes less wide and less wide and less wide and less wide? And you saw this with derivatives too. It's an idea of what if I take the limit at a smaller and smaller interval until I'm finally taking the limit at an infinitely small interval. We're going to do the same thing here in the integration process, and we're going to say, well, what if I take the area of this at a smaller and smaller and smaller interval until I finally get to an infinitely small interval. And there's a way that we're going to be able to work that into something we call an integral. If you know the function for this curve, you would be able to do what's called integration over that function, and it would give you the value for that particular area. Okay, so but you'll have to wait and see how that works. This sum of these areas is called a Riemann sum. I don't know if you've heard that term yet, but it's R-I-E-M-A-N-N. It's a Riemann sum. So you'll hear about that sooner or later. If we don't know calculus, or if there's no mathematical relationship that tells us how the force varies, the best we can do is make this kind of an estimate. So if we graph the strength of the force at each point along the path the object is moved, we create a graph like the one shown. We can draw a series of rectangles along that curve that represents an average force for that distance. As work equals force times distance, the height of the rectangle represents this average force, and the width of the rectangle represents the distance. Understand that multiplying this average force by distance represented is the same thing as finding the area of that rectangle. So finding the area of this rectangle means that you've also found the amount of work that you've done for that distance. Okay? Repeat the process of multiplying the average force and distance for each rectangle to get the amount of work represented by each rectangle. Adding the values of all the rectangles will give you the estimate of the total work. This is called finding the area under the curve. We say that the amount of work accomplished is the area under the curve of a force distance diagram. Okay. Now, objects in motion have the ability to do work, right? If I have a bowling ball rolling down the alley, the ball is in motion. It has the ability to do work on the pins, right? It's going to cause them to fall over, hopefully. So, objects in motion have the ability to do work, thus they have energy. Okay? Now, what have you heard the definition of energy is? The ability to do work. Okay? That's really nebulous to us, right? It never made any sense to me at all. What is the ability to do work? How do I quantify that? Okay? So the way that I have to think about this is that the ability to do work can be looked at by figuring out how much work caused the kinetic energy in the first place. So if I've got my baseball, again, if I do a 50 Newton force over a meter, I did 50 newtons or 50 joules of work on the baseball. That baseball now has 50 joules of kinetic energy. Okay? So the amount of stuff I do on the object is the amount of stuff that it gets. The amount of stuff I do on the object is the amount of stuff that it gets. So I don't even try to think about this idea. It's the ability to do work. I kind of look at it from the perspective of, well, what work did I have to do to give it that ability in the first place? And that helps a lot for me. If I know that I had to do 50 joules of work on that baseball to give it that 50 kinetic energy, joules of kinetic energy, I can see that, right? I can see the motion of my arm going 1 meter, and I know how large a force of 50 newtons is, or I can think of that. It's more than 50 newtons, obviously, but that's something I can see. So I can at least equate that 50 joules of kinetic energy that the baseball now has with something that means something to me. Okay? The ability to do that amount of work, well, I gave it that ability by doing this, so it has that ability to do work. Okay? So if I know how much work I did on it, I have an idea of how much work it now has the ability to do. So that's how I look at this idea of the ability to do work. But objects in motion have the ability to do work. The amount of work a moving object can do, and so the amount of energy it has is proportional to, obviously, the amount of motion the object has, which we call what? The velocity, right? Okay, so if I have something traveling at 10 meters per second, and I have something traveling at 100 meters per second, and they have the same mass, which one's going to be able to do more work? This one, right? So the amount of motion the object has, the amount of work I can do is proportional to my velocity. Now, if I have two things traveling at 100 meters per second, and this one's 1 kilogram, and this one's 100 kilograms. Which one of these things is going to do more damage?
100 kilograms?
Yeah, okay. So the amount of work something that's moving can do is proportional to the mass and the velocity. The energy contained in an object as a result of its motion is called the kinetic energy. And we can easily define a way to calculate this type of energy. Recall that we've said, oops. This will be the last thing we do today. Recall that we've said that the amount of energy an object has equals the amount of work performed on it in generating the motion. We know that to accelerate an object, we must apply a force, a net force. Force net equals mass times acceleration. We further know that the force required to accelerate the object has to be applied over a displacement. So, the work required to create the force, or to create the acceleration, is going to be, we got time. Force times distance equals, and I've left the cosine out here, that's okay, so I know that force times distance is now mass times acceleration times distance. We may not know the acceleration, but we'll often know the other features of motion. If we don't know the amount of time involved, we know that the acceleration is related to the velocity of displacement by this, right? If we don't know the time, we know v squared equals v0 squared plus 2a times x minus x0. And we know that this is the same thing as the distance, right? So acceleration is going to equal v squared minus v0 squared over 2d. So if I isolate 2d from this equation here, I subtract v0 squared, that's on top, I divide by 2d, and acceleration equals 2d. And now let's plug that into work equals force times distance equals mass times acceleration times distance. So I put v squared minus v0 squared over 2d here, and work equals mass and distance cancels out, v squared minus v0 squared over 2. So it equals, work equals 1/2 mv squared final velocity minus 1/2 mv squared times my initial velocity. Okay? And if we say that my initial velocity is 0, that drops out, and we get a general definition of kinetic energy that is kinetic energy equals 1/2 mv squared. Well, this says work equals 1/2 mv squared, but the amount of work that I do equals the amount of kinetic energy I get. So work equals 1/2 mv squared equals kinetic energy. So my formula for finding kinetic energy is 1/2 mv squared. Okay? And we'll start there next time. And by then, hopefully, I will have figured out something to do for assessment for our last unit.